This video is for lesson 20-1 about the Pythagorean Theorem. For learning goals, we're going to work on the second goal, applying the Pythagorean Theorem to solve problems. We won't worry about proving the theorem because you already have done that in previous math classes. Our real-life scenario for this activity is about a company that manufactures kites. Sarah owns a company that manufactures custom kites. Her customers go to the website and design their own kites, and then the company builds them. Many of the customers don't know the correct names for parts of a kite, and so Sarah is creating a web page to educate them so they can better communicate. Because kites include right triangles, the Pythagorean theorem is useful for analyzing the different dimensions in a kite. Here we have an example picture of a kite, and then this line drawn right down the middle of the kite is called the spine of the kite. That's one of the vocabulary words that the company needs to tell its customers. How long is that spine? We can find that length using the Pythagorean theorem because there is a right triangle in the kite, and we know the length of the legs of the right triangle. The short leg is 12 inches. The longer leg from here to here is 35 inches, and the spine is the hypotenuse of the kite. We could find that spine using the Pythagorean theorem. It's a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. A stands for the shortest leg. In this case, that's the 12 inches. B is the other leg, the 35 inches, and the letter C always represents the hypotenuse. So to find that unknown distance, we make substitutions. 12 squared plus 35 squared, and that's equal to C squared. Now we'll take a calculator and figure out what 12 squared plus 35 squared is. It makes 1,369, and then to solve for C, let's take a square root. The final answer is 37 inches. That's how long the spine of that kite is. And we found that distance using the Pythagorean theorem, which is a theorem that applies to all right triangles. It explains how the three sides of a right triangle are related to each other. Pause the video for you to finish copying this example. Next, let's skip ahead to the Check Your Understanding section and look at problem 5. We're not going to look at problem 6. A Pythagorean triple is a set of three non-zero whole numbers that satisfy the Pythagorean theorem. That means that these are whole numbers that could be sides of a right triangle. Explain why the numbers 3, 4, and 6 are not a Pythagorean triple. To be a Pythagorean triple, the numbers have to work if you substitute them into the Pythagorean theorem. So let's see what happens when we do. The shortest one we'll put in for A. The next largest number we'll fill in for B. For the letter C, we'll put in the largest number. We want to know if these are equal, so I'm going to put in equals with a question mark on top. And now let's solve this. 3 squared is 9. 4 squared is 16. Over on the other side, 6 squared is 36. Again, we're asking the question if they're equal. We're not just saying that they're equal until we actually know it. 9 plus 16 is 25. Is 25 equal to 36? The answer is no, and that's why the numbers 3, 4, and 6 are not called a Pythagorean triple. Let's contrast that with the numbers 6, 8, and 10. Do those three numbers form a Pythagorean triple? To find out, use 6 for the A, use 8 for the B, and use 10 for the C, and check to see if they are equal. 6 squared is 36, 8 squared is 64. 10 squared is 100. Are these equal? 36 plus 64 is 100. So we can see that these are equal to each other. The numbers 6, 8, and 10 satisfy the Pythagorean theorem. They would be called a Pythagorean triple. They are numbers that could form the sides of a right triangle. Let's skip to this next question. One of Sarah's customers designed the rhombus-shaped kite shown. Because this is a rhombus, all four sides are congruent. I'm going to put these little marks on the four sides to show that they're all the same length. Here we have some additional vocabulary. Again, from this corner to this corner, that was called the spine. But then going across the center, the vocab word in kite building is that that's a spar. The diagonals of a rhombus are perpendicular, and so we have the 90-degree angle box. And notice that creates right triangles. Now, what are we actually asked here? Number 7, the length of the spine from A to C is 28 inches. If it's 28 inches all the way from top to bottom, then this is 14 and this is 14. The length of the spar, which is the DB, is 24. Well, that means that this is 12 and this is 12. We could find one of the sides of that rhombus. Focus your attention on just one of the right triangles and do your best to ignore the other 3 of them. Just look here at this top left triangle. We don't know how long its hypotenuse is. We could put a variable on it like c and use the Pythagorean theorem to find that length. Once we know the length, if you times by 4, because there are 4 equal sides around the rhombus, that would be the perimeter of the rhombus. And that's what we're asked to figure out. What is the perimeter? So let's find that. A squared plus b squared equals c squared. What do you put in for A? It's the 12. What do you fill in for the B? It's the 14 equals c squared. Now take a calculator and figure out 12 squared plus 14 squared and write down the answer that you get for c squared. And then find c. I'm going to pause the video for you to finish this question. I got 18.4 inches as the length of one side of the kite. Now you may have even worked ahead and figured out the perimeter by multiplying by 4. Let's see what we get when we do that. It's 73.6 inches. We were able to find the perimeter of the kite by first finding one of the sides of the kite and then multiplying by 4. I'll pause the video for you to finish copying this example. Let's skip ahead to the check your understanding on the next page. We're going to skip number 8 and work on number 9. How high up a vertical wall will a 24-foot ladder reach if the foot of the ladder is 10 feet from the wall? Show the work. It'll help if we make a drawing of this. From the side, a vertical wall is just a line going uphill. Let's draw horizontally to be the ground. Now from the side, there's a ladder running diagonally. It touches the ground right here, and it touches the wall up there. We are told that the ladder is 24 feet, and so I'm going to label 24 feet on that diagonal line. We're told that the base of the ladder is 10 feet from the wall, so it's 10 feet from there to there. How high up the wall will it reach? So the thing we don't know is how far up this is. We need a variable for that. Because we're going to use the Pythagorean theorem, it makes sense to use one of the letters of the alphabet in the Pythagorean theorem. I'm going to choose B. We have a squared plus b squared equals c squared. A is the shortest side of the triangle. Let's fill in 10. Keep the letter B. And then for the letter C, that's the hypotenuse of the triangle. Fill in 24. Now you can see why I chose the letter B for this side. Because A is the shortest side, I knew that I wanted the 10 to go in for A. That's why I chose B to be the other leg of the triangle. 10 squared is 100, plus B squared equals, and then 24 squared is 576. Subtract 100 from both sides, and we get B squared equals 476. Now use your calculator to do the square root of 476 to see what you get for B. I'll pause the video for you to do that. It's 21.8 feet. The ladder's 24 feet long, but when you put it diagonally, it doesn't reach 24 feet up the wall, only 21.8 feet. So those were the notes for lesson 20-1, where we're using the Pythagorean theorem to work with right triangles. The Pythagorean theorem is a squared plus b squared equals c squared. A is the short leg, b is the other leg, and c is the hypotenuse.